Everybody knows how to multiply two real numbers together. Here I've got a number line, and if I take two real numbers from this number line, it's very easy to multiply them together. For example, here's 3 and here's 4, and of course we all know that 3 times 4 is just 3 copies of 4. 4 plus 4 plus 4, it's 12. But what if instead of looking at one dimension, like a number line, we look at 2 dimensions? If we introduce a second number line passing through the original one, well, now we're looking at what's called the Cartesian plane. This is 2-dimensional space, and any point in this space can be identified by 2 numbers. For example, this point here can be identified by 1, its horizontal position, and 3, its vertical position. Together, these 2 numbers describe the position of this one point. Given how basic and important the operation of multiplication is, surely we should be able to find a meaningful way to multiply 2 points in the plane. And so today we're going to learn how 2 objects in the plane can be multiplied. I say objects because they're not necessarily numbers at this point, right? They're pairs of numbers. And in so doing, we'll also learn how angles are defined in 4 dimensions. Okay, so here's a little sketch of 2-dimensional space, and let's draw 2 points in this space. We'll say that the coordinates of this point are A, B, so its horizontal position is A, and its vertical position is B, and we'll say that this point down here has coordinates C, D. To start making sense of what it could mean to multiply these 2 points together, let's go back to multiplication on the number line and view it from a slightly different perspective. On the real number line, of course, we can view each number as being a point, but we could also view each number as being a directed segment coming from 0. So for example, while we could think of 1 as just being this point on the number line, we could also think of it as being the directed line segment which starts at 0 and has a length of 1. It goes forward 1 unit. I'm drawing this above the number line just to make sure that you can actually see it, but in theory it's on the number line. Similarly, we could view the number 3 as being the point at that position on the number line. But again, we could also view it as being a directed line segment starting at 0 and having a length of 3, going in that positive direction for 3 units. If we view these numbers as being directed line segments, we can view multiplication as just being the product of their magnitudes. The magnitude of this segment, its length, is 1, and the length of this other segment is 3. When we multiply 3 times 1, we multiply these magnitudes together, and of course in this case we get 3. If we take this perspective in the 2-dimensional case, then we could view these points in the plane as arrows coming from 0, in this case the origin, coming from 0 and going to the point. So instead of viewing this as a single point, AB, we could view it as what's called a vector, going from the origin to that point, AB. And we could view the point CD as a vector, going from the origin to that position, CD. Vectors, generally speaking, are things with direction and magnitude. Of course, these arrows have direction, they each point in different ways, and they have magnitude, they have lengths. And from our prior discussion, we're thinking perhaps we can define multiplication between numbers like this, in this case vectors, by multiplying their lengths together. Then, if we call this vector u and this vector v, of course, we need to figure out what the heck the lengths of these vectors are. Thankfully, that's pretty easy if you recall the Pythagorean theorem. Let's say this is that vector u, which had components a and b, and let's have it be the hypotenuse of a right triangle. So we'll drop this perpendicular leg down, and bam, just like that, we create a right triangle. Since u is the vector going from the origin to the point AB, we know the leg lengths of this right triangle. The horizontal component is A, so that's the length of the bottom leg, and the vertical component is B, so that's the length of this leg on the right. The hypotenuse, of course, is the vector u, and its length is denoted with absolute value bars. So then, applying the Pythagorean theorem, we know that the square of the length of the hypotenuse is equal to the sum of the squares of the legs. And then taking square roots on both sides, we see that to find the magnitude of one of these vectors, we just have to take the square root of the sum of the squares of the coordinates that describe their positions. In particular, the coordinates a and b, of course, describe the position of what we call the terminal point of the vector u. It starts at the origin, that's its initial point, and it goes to the terminal point ab. And we use those coordinates in order to find the magnitude or length of the vector u, and of course we could carry out a similar calculation to find the magnitude of the vector v. In particular, the magnitude of the vector v would be the square root of the sum of the squares of the coordinates of its terminal point. That is the square root of c squared plus d squared. Alright, now that we understand the magnitude of vectors, we can try to define multiplication. What should it mean to multiply a vector u in two-dimensional space by another vector v in two-dimensional space? Well, we should just multiply the magnitudes of the vectors together. The magnitude of u times the magnitude of v. This works very much like multiplication of real numbers on the number line. Unfortunately, as simple as this is, it is not quite right, because this is ignoring something very important, which is direction. Remember, these vectors have both direction and magnitude, and this definition of multiplication only involves the magnitude. Indeed, the direction needs to be considered as well, just like it has to be considered in the multiplication of single real numbers. Back on the number line, if we think about numbers still as being arrows pointing in their direction, then when we multiply two real numbers together, we get a positive if the numbers point in the same direction. For example, 2 and 3 can both be represented by these arrows pointing to the right of 0. They point to the same direction, and so 2 times 3 is a positive number. Multiply their magnitudes, which is 6, and it's positive, so that's good because the arrows are pointing in the same direction. On the other hand, if we multiply two numbers that face opposite directions, like multiplying 3 by -2, then the answer needs to be negative. -2 and 3 face opposite directions, so -2 times 3 is not just 6, the product of the magnitudes, it's -6. On the other hand, of course, if we do -2 times -3, those two numbers face the same direction, so when we multiply them together, we again get a positive number, just the product of the magnitudes. It would again equal 6. So we need to take this idea into our definition of the multiplication of vectors in two-dimensional space. If two vectors face the same direction, then we just have to multiply their magnitudes together. We can imagine that we then multiply that by +1. Just to draw a contrast, for when the vectors face in opposite directions, we need to negate the answer. We need to multiply by -1 after multiplying those magnitudes together. Unfortunately, this too leaves us with some questions. If two vectors point in the same direction, then we would say there is a 0-degree angle between them. But if they point in opposite directions, there is a 180-degree angle between them. For example, these two arrows point in opposite directions. If we imagine that they were coincident, so they start at the same place, clearly you can see that angle between these arrows pointing in opposite directions is 180 degrees. The problem is that if we're looking at vectors in two-dimensional space, these aren't the only possibilities. We could have two vectors with a 0-degree angle between them if they point exactly the same direction, or they could have a 180-degree angle between them if they point in opposite directions. But of course, there's also a ton of possibilities between 0 and 180, and we need to account for all of those as well. So really what we need for our multiplication of vectors in two-dimensional space is this sort of multiplicative factor or dial that's going to multiply by +1 if the vectors face the same direction. It's going to multiply by -1 if they face in opposite directions, but then it can also take on any value between 1 and -1, and to the degree which the vectors face the same direction, this multiplicative factor we need should be closer to +1. If the vectors face nearly opposite directions, then our multiplicative factor should be closer to -1. So our definition of multiplying two vectors together should be the product of their magnitudes and then multiplied by this additional multiplicative factor that we've got to figure out. Thankfully, exactly the sort of function we're looking for exists. It's called the cosine function, and it's going to be exactly the multiplicative factor that we need to finish our definition. As a quick intro to what the cosine function is, it's based on right triangles. Say we have a right triangle here, that is a triangle with a right angle, and let's call this acute angle of the triangle theta. Then let's name the sides of the triangle. This one will be A because it's adjacent to this angle. This side will be O because it's opposite the acute angle. And this side will be H for hypotenuse. Then cosine is a function written like this, cos. And what we put in the function is an acute angle of a right triangle, cosine of theta in this case. What it will output as a value is the ratio of the adjacent side to the hypotenuse, adjacent over hypotenuse. And this ratio will take on values between -1 and +1. Imagine this acute angle theta was approaching 0, for example. So we've got this hypotenuse and this leg. The angle between them is approaching 0, so they're sort of closing in on each other. And what would have to happen for the triangle to continue being a right triangle is that the length of the hypotenuse would have to be approaching the length of this adjacent side, meaning that the ratio between them would be approaching 1. That's a degenerate right triangle because it doesn't really have three distinct sides when you look at it, but that's the intuition that tells us indeed cosine of 0 is equal to 1, just like we want it to be, because remember, we want this to measure the degree to which two vectors point in the same direction. If the angle between them is 0, that is, they point in exactly the same direction, then we want to multiply by 1. In effect, we're not adjusting anything, we're just multiplying their magnitudes together, and then multiplying by 1 doesn't change it. For other directions, aside from 0 degrees, when the vectors are pointing in different directions, we need to adjust, and the cosine function is going to do that for us. Now, based on what we've discussed, what would we want cosine of 180 degrees be? Well, in this case, the vectors are pointing in opposite directions, so we would want cosine of 180 degrees to be -1. In this case, we want to multiply their magnitudes together, but then negate it. And in fact, that is how the cosine function works. Cosine of 180 degrees is -1. It's very easy to define the cosine function for these right triangles where that acute angle theta is between 0 and 90, and you can just look at the ratio of this adjacent side to the hypotenuse. But for larger angles approaching 180 degrees, we have to be a little bit more creative. If we had a vector here lying on our horizontal axis, and this other vector, which has a pretty big angle between it and the smaller vector, the idea for the cosine function is that we would then look at this right triangle over here, where again we're able to see an angle that is between 0 and 90 degrees, and again we can just define the cosine of that angle to be the ratio of this adjacent side to this hypotenuse. The thing is, this adjacent side is going in the negative direction, and that's how we get the -1. Again, as the angle approaches 180 degrees, the adjacent side and the hypotenuse close in on each other, and so their ratio is approaching 1, except also with that negative factor, because the adjacent side is going in the negative direction. And just like that, we have arrived at a beautiful and very meaningful definition of multiplying two vectors together in two-dimensional space. The product of two vectors, u and v, where the angle between them is theta, is defined as follows. U times v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between the two vectors. I've been talking about all of this in terms of degrees because that's what people generally learn first, but it should be noted in this formula, theta, the angle measure, is typically not taken to be in degrees. It's typically taken to be in a different angle measure called radians. Now, it's not super important that you understand radians deeply, but just to quickly tell you what they are, here's a circle, and there is its center. Here's the radius of the circle. We'll say it's r. 1 radian is the angle that it takes to cut an arc of the circle with a radius length. So this is the length of the radius. If we were to cut that same length as an arc in the circle, maybe it looks like that, the measure of this central angle that cuts that radius length arc, that angle has a measure of 1 radian. So each radian cuts 1 radius length arc from a circle. The circumference of a circle is 2 pi times the radius, so every circle has 2 pi radians. So that's just a briefing on what a radian is. Every circle has 2 pi radians. It's a beautiful angle measure. Let's move on. We should try out our new definition of the multiplication of vectors in two-dimensional space. So let's sketch out a quick example and try the calculation. Here's a vector which goes to the terminal point 3, 0. Hard to see, but it goes to 3, 0. And then we'll have this other vector which goes to the terminal point 4, 4. So we've got these two different vectors in two-dimensional space. They have different lengths, they have different directions, but now we understand what it means to multiply them together. Let's try it out. So we take the first vector, which can be described with this ordered pair of its terminal point, 3, 0, and we're multiplying this by the other vector, which can be described by the coordinates of its terminal point, 4, 4. We know that to do this, we need to multiply their magnitudes together and multiply that by the cosine of the angle between them. So let's find the magnitudes of these vectors. Certainly, the magnitude of this vector going to 3, 0 is equal to 3. The magnitude of this vector going to 4, 4 can be found using the formula that we discussed earlier. It would be the square root of the sum of the squares of its components. The square of 4 is 16, so this is the square root of 16 plus 16. This is the product of the magnitudes, and we're also going to need to multiply this by the cosine of the angle between the vectors. So this is 3 multiplied by the square root of 32, but 32 is the same as 16 times 2, and we're multiplying this by cosine of the angle. We wrote this as 16 times 2 because then it's clear we can take the square root of 16 out. Thus, we would have 3 times, the square root of 16 is 4, times the 2 is still left in the square root, and we still need to find cosine theta. Finally, this is 12 root 2, and now to deal with the cosine. I'm just going to go ahead and tell you that the angle between these vectors is 45 degrees. So this is cosine of 45 degrees, or in radians, which we would more typically use, it's pi over 4. Cosine of pi over 4 you can find using a calculator, or if you know what the unit circle is, just bust that out. It is root 2 over 2. So you can see now we have 12 over 2, which is 6, and root 2 times root 2, which is 2. So we end up with 6 times 2, which is 12. So man, oh man, that multiplication is kind of complicated, isn't it? If only there were an easier way, like with traditional multiplication. Well, turns out there is. Notice when we multiplied these two vectors together, 4, 4 and 3, 0, we got 12. Can you see any simpler way we could have gotten 12 from these coordinates? Well, it just so happens that 12 is equal to the sum of the products of their corresponding coordinates. The first component of this first vector is 3. We could have taken that and multiplied it by the first component of this other vector, which is 4, and then add the product of their second components, 0 times 4. That would have given us 12. Is this just coincidence, or is this some magically way simpler way to calculate the product? Well, although it might seem like magic, it is no coincidence. This is indeed another valid way to define the product of two vectors in two-dimensional space. If the components of u are AB and the components of v are CD, then the product u dot v can indeed be calculated as A times C, the product of those first components, A times C, plus B times D, the product of those second components. This looks a whole lot simpler than this, but in fact, they are equivalent. They give the exact same answer. And although this one looks much nicer than this one, it's only because we happen to know the components of these vectors. We know the coordinates of their terminal points. If all we knew were their lengths and the angle between them, we'd certainly want to use this formula instead. And now's a good time to point out that this notation is kind of sloppy. I'm using the same notation, a dot, to represent two different things. Here, it's representing the product of two vectors. It's actually called the dot product. But then I'm using that same notation here to represent traditional multiplication between real numbers. So really, we shouldn't be using the dot for multiplication of real numbers in this context, because the dot is reserved for this, our beloved dot product that we've just derived. Our time together won't be complete unless we actually show that these definitions of the dot product of two vectors are in fact equivalent. So let's do it. To show those two definitions are equivalent, it's important that you first understand vector addition and vector subtraction. So let's say I have two vectors here. We'll call this one A and we'll call this one B. What would it mean to add these two vectors together? We can basically think of adding the vectors together as describing a sort of net total motion. So what it means to add them together is to take one of them, let's say A, and connect it to the beginning of the other one. So here's A touching the tail of B, and then draw the vector from the initial point of the first vector to the terminal point of the second vector. That's going to give us a vector that describes the net motion of adding the vectors together. And in this case, it looks like this. This would be A plus B. So there's A, we connect it to B, and then draw that vector that goes from the beginning to the end. That's their sum. The difference of two vectors, A minus B, can be described in a similar way. For the subtraction, we have to do this. Draw the vector A, something like that, and then draw the vector B coming from the same initial point. So that would look something like this. Then A minus B is the vector that starts at the end of B and goes away from B towards A. That's A minus B. If the vector went the other direction, starting at the end of A and going away from A towards B, that would be B minus A. But as drawn here, it's A minus B. Having an understanding of these vector operations, here's a triangle where I could call this side A, I could call this side B, and I could call this side C. And then, how could I express C in terms of A and B? Well, viewing these sides as vectors, I could describe C as A minus B. Imagining that it leaves B and goes in the direction of A, it's A minus B. If we imagine that it goes the other direction, everything we're going to do would still work out fine. Let's just suppose it's A minus B, though, as opposed to the other way around. And let's also say that this angle between A and B is theta. Now, for our proof that the two definitions of the dot product we've seen are equivalent, we're going to need a sort of generalization of the Pythagorean theorem that you might have heard of, called the law of cosines. The law of cosines is like the Pythagorean theorem, except it works for all triangles, not just right triangles. It tells us that in this triangle, the square of the magnitude of that side C, so the magnitude of C squared, is going to be the magnitude of A squared plus the magnitude of B squared minus 2 times the product of the magnitudes of A and B with the cosine of the angle between them. So we're just accepting this, the law of cosines, as true. You can see at the end an expression which looks very much like what we figured out for our definition of the dot product. Sorry, I didn't like what I was writing here. Let's suppose for our proof that we're using the second definition of the dot product that we introduced. So if this is a vector u, which goes to a terminal point a, b, then we're going to say that the dot product of u with u is the sum of the products of the corresponding components. In this case, since it's a u dotted with itself, the first component a corresponds to itself, so first we would multiply a times a, and the second component b also corresponds to itself, so we would multiply b times b. Thus, the dot product of u with itself would be a squared plus b squared. Note the similarity between this and what we figured out for the magnitude of a vector. The square root of a squared plus b squared is the magnitude of u. So in fact, we see here that u dot u is the square of the magnitude, since it just lacks the square root. So u dot u happens to equal the magnitude of the vector u squared. Again, this is the expression for the magnitude, just without the square root, which means it's the square of the magnitude. With all that said, we're ready for the proof. Looking at the law of cosines, it gives us an expression for the magnitude of c squared. But now we actually just realize that the magnitude of a vector squared is the dot product of the vector with itself. So we could also write the magnitude of c squared as the dot product of c with itself, and thus we'll be able to derive a different expression for the magnitude of c squared, which we'll be able to set equal to this one, and then prove the equation we desire. And again, remember that right now we are saying that the dot product is defined with that component definition, not the one with cosine that we figured out originally. So the magnitude of c squared, what is that? Well, we know that's actually c dotted with itself, funnily enough. But we also know that we can write c as a minus b. Hence, c dot c is equal to a minus b dot a minus b. Now, it can be proven, but in the interest of time, you'll have to take my word for it, that the dot product follows the distributive property. So to carry out this dot product, we can actually just spread everything out. A dot negative b dot a, and negative b dot negative b. So writing that out, we have a dot a minus b dot a, and minus a dot b, and plus b dot b. Now again, right now we're assuming the dot product is defined with this component definition, which is clearly commutative, because it just comes down to multiplication of real numbers and addition. So the order in which we do the dot product doesn't matter. That means b dot a and a dot b are exactly the same. Thus, we can rewrite this as a dot a plus, let's bring the b dot b over earlier in the expression, and then b dot a and a dot b are the same, so let's just call them both a dot b. Thus, this is minus 2 copies of a dot b. Now, the vector a dotted with itself, as we've seen, is in fact the magnitude of a squared. Similarly, b dotted with itself is the magnitude of b squared, and we will leave 2a dot b as it is. So then here is an alternative expression for the magnitude of c squared. This guy must equal this guy from the law of cosines. So that gives us this equation, which I have to zoom way out to see, and there's a lot of good cancellation here. This is from the law of cosines, this is from all the work we just did. We see the a squared magnitudes cancel out, the magnitudes of the b squared cancel out, and then we're left with this equals this. We can divide both sides by -2, and proof done. What we see here is a dot b, which I'm going to write on the left, a dot b, the dot product, which we've taken to have the component definition, is equal to this, the original geometric definition that we discussed. The magnitude of a times the magnitude of b times the cosine of the angle between a and b. And so with the law of cosines, we're able to prove those two definitions are in fact equivalent. Thank heavens. Thanks to the equivalence of these two definitions, we have a pretty nice way of finding the angle between two vectors in the plane. This isn't drawn to scale, but let's say this is a vector going to the terminal point 4, 3, maybe something like that. And then say this is a vector going to the terminal point -5, 12. Then what the heck is this angle between the vectors? It kind of looks like a right angle, but it's not supposed to. Again, this is just a rough sketch. Well, if we call this vector u and this one v, to find that angle between them, we can use the dot product's equivalent definitions. We know that u dot v must equal the sum of the products of their corresponding components. -5 times 4 is -20, and then we would add that to 12 times 3, which is 36. -20 plus 36 is +16. That's the dot product between u and v. But of course, the dot product has two equivalent definitions. So we know that 16 must also equal the magnitude of u times the magnitude of v times the cosine of the angle between them. Again, in the interest of time, I'll leave this to you to verify. The magnitude of u, you can check, is 13, and the magnitude of v, if you run the numbers, is equal to 5. 5 times 13 is 65, so then we have that cosine of the angle between the two vectors must be 16 divided by 65. And then, just like division undoes multiplication, there is an inverse function for cosine called inverse cosine, or sometimes arc cosine, and you can find it on a scientific calculator. We can take the inverse cosine of both sides here to find the angle theta between the two vectors. Theta is going to be the inverse cosine of 16 over 65. And if we punch this into a calculator, we find that the angle between the vectors is about 1.3 radians, or if you prefer degrees, it's about 76 degrees. Thus, you see from the dot product, we're able to find the angle between two vectors. So then, how do we answer that other distant question you may remember from the beginning of the video? How do we find the angle between vectors in four-dimensional space? Well, we actually just have to do the same procedure we just did. In four-dimensional space, a vector would have four components, specifying its position on all four of the fourth-dimensional axes. So if we had this fourth-dimensional vector, 1, 2, 3, 4, and we took its dot product with the other fourth-dimensional vector, -1, 0, 1, 2, just for example, using this dot product, we could find the angle between the two vectors. The dot product definition, using components, generalizes exactly the way you would expect. All we do is multiply corresponding components together and add them all up. So 1 times -1, 2 times 0, 3 times 1, 4 times 2, add it all together. That's -1 plus 0 plus 3 plus 8. So the dot product of these two vectors is equal to 10. Remember, in the calculation we just did, we also needed to divide by the magnitudes to get this cosine all by itself. The magnitudes of vectors in 4 dimensions generalizes very simply as well. In 2 dimensions, we would just take the square root of the sum of the squares of the components of the vector, and it works the same in 4 dimensions. The magnitude of this vector we can find using a generalized Pythagorean theorem, which would give us the square root of 1 squared, which is 1, plus 2 squared, which is 4, plus 3 squared, which is 9, plus 4 squared, which is 16. A similar calculation with this other vector will give us the square root of 6. And then, again, understanding that the dot product has two equivalent definitions, we have that 10 should be equal to the product of the magnitudes of these two vectors with the cosine of the angle between them. The product of the magnitudes is the square root of 30 times the square root of 6, and then of course we have to multiply by cosine of the angle between them. So then to find that angle between these two vectors in 4 dimensions, all we would do is take 10, divide it by the product of the magnitudes, and then we would take the inverse cosine on both sides. So we would have the inverse cosine of 10 divided by the square root of 30 times the square root of 6. We then get a fourth dimensional angle of about 42 degrees. Phew, boy, well, that was fun. I think I need to go sip some hot tea. Let me know in the comments if you have any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
From my fate, twisting to escape this. Climbing out of my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Erase the tune of words and just how I say shit. And let me speak my poetry to your face. It's not intimate if you ain't listening. Not infinite if you ain't really in it.